This is the supplementary video for lecture 15, where we will provide the solutions to the leftover 3 problems in exercise 11. So I will only record the solution for number 25, and I will use the videos I made in the last semester for the other 2 problems. Okay, so let's look at problem 25. So the first sentence reads, water is leaking out of an inverted conical tank at the rate of 10,000 cubic centimeters per minute. And at the same time that the water is being pumped into the tank at a constant rate. All right, so this is a very long sentence and it has multiple parts. So let's just read each part very carefully. So first, water is leaking out of an inverted conical tank. So what exactly does it mean for us to have an inverted conical tank? Well, first, let's understand what's a conical tank. So a conical tank basically looks like this. So this is going to be a conical tank. Well, then an inverted conical tank will basically be the inversion of the conical tank we have over here. All right, so this is basically the first part. And now we know that water is leaking out from the tank. So which means originally there is water inside, but now it's leaking out. And then we are given the rate of its leaking out. But moreover, we know also from the next part of the sentence that water is being pumped into the tank at a constant rate. So this means we have got water in for some rate over here. All right, so that's basically what you should know from the first very long sentence. Now let's look at the second sentence. So we know that the tank has height 6 meters and the diameter at the top is 4 meters. So this basically means, well, we have got a cone and then whose height is going to be 6 and whose diameter at top is going to be 4. So this is basically what the sentence tells you directly. Okay, so now the next sentence, if the water level is rising at the rate of 20 centimeters per minute when the height of the water is 2 meters, and we need to find out the rate at which water is being pumped into the tank. All right, so that's basically what this sentence says. Well, first, no important word is that the water level is rising. Yeah, to make the water level rising, so the rate at which water is being pumped into the tank must be greater than the rate where water is leaking out of the tank. So let me start by drawing the inverted conical tank, which roughly looks like this. So this will be the top. And let's draw the sides roughly like this. Okay, so this is my tank. And now we know that there's water inside. So let me actually use blue to mark that the water is inside. How do I control this one? Okay. Yep, so this is actually water inside. Okay, so this is my inverted conical tank. Okay, what do we know about this cone? So first, we know about its diameter. So the tank has got diameter 4 and the height being 6. Right. So, well, what does that just tell us? So this will tell us that the water cone, namely this smaller cone inside, will have the similar ratio. So in other words, well, the diameter of the water cone and the height of the water cone inside over here, they should also obey the same ratio, namely it will be 4/6. So this will be an important piece of information. All right, so what else we know? The water level is rising at the rate. So this means the height of this water cone, so this is increasing. So, well, it's probably a good time for us to introduce notations. So let's first start by introducing the height. So let h be the height of the water cone. So then we know that dh over dt, so this is actually going to be 20 centimeter per minute. So that's what we know. So mark on the graph so that this number, so or this distance is called the height of my cone over here. Okay, so let me adjust these arrows in better location. So this will be my height over here. Okay, so moreover, we know that the diameter and the height has got a ratio 4/6. So this will mean that my radius and the height is going to have the ratio of 2/6. So yeah, let me actually start by declaring variables. So let R be the radius of the water cone, and the diameter, namely 2r of the water cone, divided by h. So this will have the same ratio as 4/6. So this will tell me that r is going to be 1/3h. All right, so this is actually what we know from here. Okay, so finally, if we let V be the volume of water in the tank, then the volume is given by 1/3 pi r squared h. So this is actually what we know about the volume. And now we know that r equals to 1/3 h, so that we could actually write it as 1/3 pi times the square of 1/3 h times h. That way we got V equals to 1/27 pi h cubed. So that's the volume in terms of the height. Okay, so that now we want to figure out the rate where water is pumped. Okay, so from this relation, I will be able to get the rate of change of the volume. So namely dV/dt. So this is going to be equals to 1/27 pi times the derivative of h cubed versus t. But using the chain rule, I will get 1/27 pi times 3h squared times dH/dt. Simplifying, I will get 1/9 pi h squared then times dH/dt. So this guy is going to be the rate of change of the volume of the water inside over here. And now it seems that we know everything. So we know dH/dt be in positive 20 centimeters per minute. And we also know the height is going to be 2 meters, but watch out the units over here. So you need to actually unify the units when you try to perform any computations. Otherwise, your numbers might be wrong. So let's say that when h equals to 2 meters, which is going to be close to 200 centimeters. So we know that dH/dt equals to 20 centimeter per minute. So this follows from the sentence that if the water level is rising at a rate when the height equals to 2 meters. So that's actually how we can write this. Okay, so this will tell us the rate of the change of the volume will be 1/9 pi times the square of h times dH/dt, namely 20. Let's count how many zeros we have. So we have 1 0 over here and 2 0 over here, but we need to square it. So that will means 4 zeros over here. So 4 zeros plus 1 0, that will be 5 zeros. So we need to have got 10 to the 5th over here. And then whatever remains will be 1/9 times the square of 2 times 2. And the answer will be 8/9. And remember, there's also a pi over here. So this is going to be the rate of the change of the volume, namely 8 pi over 10 times 10 to the 5th. And the unit will be cubic centimeter per minute, because what we are doing here is to multiply 2 copies of centimeters and 1 copy of centimeter per minute. So that's how we get this unit over here. Okay, so this is the rate of the change of the volume. All right, let's now see what we want. We want to figure out the rate at which the water is pumped in. So let P be the rate at which water is pumped in. Then we know that P minus 10,000, so this is actually the rate at which water is leaking out. We know that P minus 10,000, so this is going to be equals to 8 over 9 pi times 10 to the 5th power. So this way, we see that P equals to 8 over 9 pi times 10 to the 5th, and then minus, well, 10,000, there will be 4 zeros over here. So that way we get 10 to the 4th power. And the unit will be cubic centimeter per minute. Okay, so this is precisely the number we want. So we need to figure out the rate at which water is being pumped into the tank. And now we get the rate. The rate is precisely this number. So because this class, we do not allow calculators. So when you try to formulate the answer, you just formulate it in this way. So the water is pumped into the tank at the rate of 8 pi over 9 times 10 to the 5th minus 10 to the 4th cubic centimeters per minute. All right, so that will finish this problem. So you see that, well, the order of this solution is completely different to the order of the information given to you. So you see that we first used this piece of information, and then we use this piece of information to figure out the radius. Then together with these two information over here, so we figure out the volume, and together with the change of the rate of the volume. And then after we figure out this part, we use the fact that water is going to be 2 meters to figure out the rate of change of the volume. Then, well, the first information, namely this 10,000 cubic centimeter per minute. So this information is only used in the very last step over here. So this is how related rates problems are in general difficult. So you need to figure out the correct logical order to solve each problem. Please definitely practice this skill of sorting out the correct logical order, and you will find it extremely useful in your life. So for the remaining 2 problems, I found that I have made the complementary video for these 2 problems last semester. So allow me to be lazy and reuse those videos directly. Now let's look at the problem statement. A baseball diamond is a square with side 90 feet. A batter hits the ball and runs towards the first base with a speed of 24 feet per second. So part A asks, at what rate is his distance from the second base decreasing when he's halfway to the first base? And part B says, at what rate is his distance from the third base increasing at the same moment? Okay, so this is the problem statement. Okay, so fortunately, the problem provided a picture. So this is the square of the baseball diamond. And then the batter hits the ball at this spot, then starts running to the first base. We are interested in the change of the distance from the batter to the second base and the change of the distance from the batter to the third base. So as you could see, as the runner moves forward, so the distance to the second base is decreasing and the distance to the third base is increasing, as you could see from the picture over here. And we need to understand how fast such distances are changing. Okay, let's start introducing the notations. So since we are interested in this distance, it is quite natural for us to choose by x to be the distance between the batter to the first base. And we know that this distance is going to be 90. As a result, we have a formula for the distance between the batter and the second base. So from Pythagorean theorem, you see that this distance is x squared plus 90 squared. All right, so this will help us to solve part A. Okay, so for part B, so if we are interested in this distance, but then, well, this distance is precisely the hypotenuse of the right triangle formed by the side of the baseball's diamond together with this distance. And we know that this distance is 90 minus x. So then by Pythagorean theorem, we will be able to tell that the distance to the third base is simply going to be 90 squared plus 90 minus x squared. Okay, so these are the relations we want to find. Now let's actually start by writing down all the details. So, so we would let x be the distance from the better to the first base. So then also let's let y be the distance from the better to the second base. Then geometry we have analyzed before will tell us that y equals to square root of x squared plus 90 squared. So apply dy over dt on both sides. Left-hand side is precisely dy over dt. So for the right-hand side, you need to use chain rule multiple times. So the first top layer, well, we view the outer function to be the square root function. So the derivative of the square root function is simply 1 over 2 times the square root. And then we need to evaluate this guy at the inner function, then times the derivative of the inner function. So for the derivative of the inner function, we need to use chain rule again. So derivative of 90 squared, this guy equals to 0. And derivative of x squared, so you need to view the square function as the outer function. So its derivative is simply 2 times the argument, so namely 2 times the inner function. Then chain rule will tell me that the derivative with respect to t is simply going to be 2x times dx over dt. Okay, so notice that this 2 cancels out with this 2 over here. So that way we can write our final solution for dy over dt as x divided by square root of x squared plus 90 squared times dx over dt. Okay, so this is the relation between dy over dt and dx over dt. Okay, so to answer part A, we are interested at the time when the better is halfway through the first base. So this means x equals to 90 over 2, which is 45, and the unit is in feet. And moreover, we know that dx over dt equals to minus 24. The unit is in feet per second. So notice that I've chosen the dx over dt to be negative because x is decreasing. Okay, so with all this information, we see that dy over dt is simply going to be 45 divided by 45 squared plus 90 squared times minus 24. Also, 45 squared and 90 squared are very large numbers, and we would like to avoid computing such large numbers. Okay, so and this can be done by using the following trick of factorization. We will write 90 squared as the square of 45 times 2. So this is simply because 90 equals to 45 times 2. Then, while the power of a product is distributed into each factor, so 45 times 2 squared is simply going to be the 45 squared times 2 squared. And this will simply be 45 squared times 4. This will tell me that 45 squared plus 90 squared, this is simply 45 squared times plus 45 squared times 4. And if you factor out the common factor, 45 squared, then what I get is 1 plus 4, and the answer will be 45 squared times 5. Okay, this will further tell me the square root of my denominator is simply 45 times root of 5. Okay, so this makes the arithmetic much easier because what I am having over here is simply 45 times minus 24 divided by 45 times root of 5. And you see that the common factor 45 cancels out. The answer is minus 24 divided by 5. The unit is feet per second. Okay, so this way we can answer the first part A. So the answer is, so the distance between the better the second base decreases at the rate 24 divided by root of 5 feet per second. Okay, so this is the answer to part A. To handle part B, we will set z to be the distance from the beta to the third base. Then from the geometry we have discussed in the very beginning, we see that z equals to root of 90 squared plus 90 minus x squared. Okay, so if you apply d over dt on both sides, left-hand side is dz over dt, and the right-hand side, I need to use the chain rule again, similarly. So the square root function, derivative of square root function is 1 over 2 square root evaluated at the inner function. Okay, so then I need to take the derivative of 90 squared plus, so I will rewrite 90 minus x squared as x minus 90 squared. I am allowed to do so because 90 minus x itself is going to be minus 1 times x minus 90. So if you want to square both sides, so it's called 90 minus x squared equals to minus 1 squared, x minus 90 squared. So this is going to be x minus 90 squared. So I can switch 90 and x over here whenever that square is upward. Okay, so this is why I am writing x minus 90 in this location. Now let's compute the derivative of the inner function. Well, the derivative of 90 squared is simple. It's simply going to be 0. For the derivative of x minus 90, we need to use another round of the chain rule. So it will be the square function as the outer function and x minus 90 as the inner function. So chain rule tells me that the derivative of x minus 90 squared is simply going to be 2 times the inner function times the derivative of the inner function. But derivative of the inner function, it is precisely dx over dt because the derivative of minus 90 equals to 0. Okay, so this is the derivative of this guy here. And notice that this 2 and this 2 will cancel out eventually. So at the end of the day, dz over dt will be x minus 90 divided by root of 90 squared plus 90 minus x squared times dx over dt. All right, so this is the derivative of z respect to t. Okay, since part B is asking the rate of change at the same moment as part A, so this means x is still going to be 45 feet. And moreover, dx over dt, well, this is still going to be minus 24 feet per second. So then you see that dz over dt, so this is simply going to be 45 minus 90 divided by root of, so 90 squared plus, well, 90 minus x is 90 minus 45. Well, 90 minus 45 is still going to be 45. So there will be the same guy in the denominator, 90 squared plus 45 squared. And then this whole thing times minus 24. Okay, from the computation we have done in part A, we see that the denominator is precisely 45 times root of 5. And then this will be, the numerator now becomes minus 45. And then this whole thing times minus 24. So the answer for dz over dt is precisely positive 24 divided by root of 5. And the unit is feet per second. Okay, so now we are ready to formulate the answer. So the distance between the batter and the third base increases at the rate 24 divided by root of 5 feet per second. Okay, so this is the answer to part B. Okay, let's look at number 22. A boat is pulled into the dock by a rope attached to the bow of the boat and passing through the pulley on the dock. that is 1 meter higher than the bow of the boat. Okay, what a mouthful of words. If the rope is pulled in at the rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, fortunately, we are given the picture so that we can imagine what's going on. So let's say we are pulling the rope from here. So then the boat is going to be moved a little bit forward. So in the next moment, so you see that the boat is moved over here and the angle of the rope actually changes. And it's precisely because the angle of the rope changes a little bit. So the speed of the boat will not be synchronized as the speed of the rope. Okay, so to solve this problem, let's draw the picture in this way. So we know that the height of the bow is 1 meter less than the height of the pulley. So this is the 1 meter. And this boat is moving along the horizontal line while the rope is actually moving along this direction. So let's set x to be the distance between the boat and the dock. And let L be the length of the rope between the boat and the pulley. So then this information, the rope is pulled in at a rate of 1 meter per second. So this is basically the change of the length of the rope. Because at the next second, so if let's imagine 1 second has passed, and this part of the rope is pulled 1 meter backwards. So as a result, this length will change by 1 meter. So this is why this 1 meter per second is really the change of the length, and it's not change of x. And we need to find the change of x from the change of the length. Okay, so that's basically what's going on. Now let's start solving the problem. And remember, you always need to declare your variables. So let x be the distance from the boat, or from the bow of the boat to the dock. And let L be the length of the rope between the pulley and the bow of the boat. Okay, so from geometry, you could see that, or from Pythagorean theorem, you see that L squared equals to x squared plus 1. So if you differentiate on both sides, so you see that 2L times dL over dt is going to be the same as 2x times dx over dt plus 0. All right, so then you cancel out the 2, and then you will be able to see that dx over dt equals to L divided by x times dx over dt. Okay, so this is the relation between the rates, and now let's look at what we are interested in. We are interested in the moment where the boat is 8 meters from the dock. So at that moment, again, from this picture, you see that the L is precisely going to be a squared plus 1 squared taking the square root. All right, so this is going to be my L and X to be plugged in the formula over here. Now let's write that down. When X equals to 8 meters, you know that L equals to square root of 8 squared plus 1 squared. So this will be 8 squared equals to 64, and 64 plus 1 equals to 65. So L is going to give me root of 65, and the unit is meter. And this is a little bit above 8. We also know that the length changes with the rate of minus 1 meter per second. And again, this is negative because L is decreasing. Then we know that dx over dt equals to L root of 65 divided by x, which is 8, and times dl over dt, which is -1. So then this will give me minus root of 65 divided by 8. And the unit is meter per second. Okay, so this is what we need. So we need to find the change of x. And as you could see, the x is negative because this distance is decreasing. All right, but to answer the question, you should actually answer it in the correct way. So because we are asked how fast is the boat approaching the dock, so that way when we formulate our answer, we should not take taking the minus sign. So the answer is the boat is approaching the dock with velocity root of 65 divided by 8 meter per second. Okay, so that's the answer to number 22.